Well, here we go again with another video in our Common Core Algebra 2 series. Tonight's focus is on using regressions to find equations. Now, this is not going to benefit you unless you pause it and go get your own calculator and are working along with us. As you realized in the stats section, this is a ton of new calculator manipulations. So grab it and play along. So our common theme tonight, we will find equations given sets of points. Each example will be a different method. So I'm going to go through several examples. Each one will be slightly different. So here's our first big definition. A regression gets us a function of best fit. That means it does not necessarily pass through all of the points in the table, but it comes as close as possible for that type of function. That's why it's a best fit function. It's not going to hit every single point. It's going to get close, but not all of them. A regression does not get you an exact equation. It is simply a best fit function. Okay, so let's be familiar with some other names. They will typically refer to this as either a regression line or function, a regression, or a best fit function. So the first example, I am going to get the exact equation of a line. Okay, so we do this with the point slope formula, which we talked about back in the beginning of the school year, and obviously you've done a ton of in geometry and algebra 1. That's our y minus y1 equals m times x minus x1. And you'll recall that that x1 and y1 are actually the point that you know. And then, of course, you'll need the slope formula. So m equals the change in y, y2 minus y1, all over x2 minus x1. Okay, now again, this is getting me the exact equation. So let's go ahead and practice with an exact equation. I need to first find the slope between these 2 points. So I'm simply going to say 4 minus, now be careful here, it's a negative 2 all over 20 minus 5. Now, of course, those 2 negatives touching is going to make a positive, so I'm going to go with 6/15. Now, you can always reduce that if possible. Those are both divisible by 3, so in fact, I'm going to call that 2/5. Now that I have my slope, that's going to go in my m, I can pick either point that's on this line. It really doesn't matter, either the 5, negative 2, or the 24. So I'm going to go with the 5, negative 2. So y minus negative 2 equals my 2/5 times x minus 5. So I'm going to say that's really y plus 2 equals 2/5 times x minus 5. Now let's go ahead and solve for y. It's a little good practice here for us. When I multiply this 2/5 through, so that's y plus 2 equals 2/5 x minus, picture this as 5 over 1. So when I multiply fractions, on top I get 10, and on the bottom I get 5. So I'm going to say that's y plus 2 equals 2/5 x minus 2. Subtract that 2 over, and y equals 2/5 x minus 4. Now let's go ahead and box that in. That is the exact equation that goes through those 2 points. It is not a best fit line. It is truly the exact equation. Okay, so example number 1, let's go ahead and title this linear regressions. So now we are getting a line of best fit. Yes, we do need to stick these 2 scatter plots, in our notes here. So just stick a bunch of dots going up, a bunch of dots going down here. So if I were to draw on the line of best fit, and that's what you need to do too, it's not possible to have one line go through every single point. That's why we make a line of best fit, aka a regression line. So I'm going to predict my line is going to go like that. I should have some points above and some points below. Now you'll notice, let's go ahead, what is the slope of this line? Well, I don't know the exact number, but what I do know is that it is a positive slope. And we're going to go ahead and draw in the regression line or line of best fit in the second one. So again, I should have, approximately half the dots below, half the dots above. And I don't know the slope for sure, but I do know that that slope is negative. So as we talk about this linear correlation coefficient, we do have to make sure something is turned on our calculator. So that's why you need your calculator handy. You need to have this ready for class tomorrow, and you have to practice with it. So what we have to turn on is something called the diagnostics. If you have a TI-84, okay, and this should be in your notes, you have it written down and you've turned it on your calculator, and it's an updated TI-84, you can simply go to the mode and you can scroll down and it should say at some point Stat Diagnostics, and you basically just need to make sure that is turned on. Okay, if you have a TI-83 and it does not have that, or maybe you have an 84 that does not have that, these are the buttons you are pressing. Again, jot it down so you know how to physically turn this on your calculator in case it gets shut off. You need to go to second 0. Okay, and that should open the catalog. That is every piece of information in your calculator. You need to scroll down until you find the D's and it says Diagnostics on. You probably need to hit enter twice until it says done, and then you have yours turned on. So you might be thinking, why is this so important? Well, what it does is it turns on this R value. So again, let's get this in our calculators as well. The R value is called the correlation coefficient. And I take that back, it's actually called the linear correlation coefficient because it is only used for lines. So let's get that highlighted. It is the linear correlation coefficient. And this tells you how closely your data is related. That R value needs to fall between -1 and 1. The closer it is to -1 and 1, the stronger it is, the stronger correlation there is. And the closer it is to 0, the weaker it is. Again, this should be all in your notes, nice and neat. So the closer you are to 1 or -1, the stronger. The closer to 0 is how weak it is. It also tells you the slope of your line. Okay, if your R value is 0.999, the slope of your line is positive, and there is a strong correlation there. So let's go ahead and take a look at our first linear regression. Biologists are trying to create a least squares regression, so another name for linear regression, equation, another name for line of best fit, relating the length of the steelhead salmon to their weight. 7 salmon were measured and weighed with the data below. So you'll notice in the table, what you need to copy down is you have the length in inches, and here are the length of the salmon, and the weight of the salmon in pounds, and those units are important. So part A says determine the least squares regression in the form y equals ax plus b for this data. Round all coefficients to the nearest hundredth. So here's what we do. We're simply putting the first row always in L1, the second row in L2. Go ahead and label that. Once you have it nicely typed in your calculator, and again, you're playing along here, so you obviously went to Stat Edit, you're going to arrow over to Calc. We are no longer doing stats. You are choosing a linear regression number 4. Notice it says in the form of y equals ax plus b. You will notice there are 2 that say linear regression, one number 4 and one of number 8. This one says in the form of ax plus b. I always pick number 4 just to be safe. When you turn it on, your x list should be L1. Your y list will have to be L2 because you entered in 2 columns of information. If you have the old calculator, when you pull up linear regression, you're going to have to hit L1, comma, L2. Okay, so again, that's if you have a TI-83 or an 84 that's not updated. Once you hit enter, you should get all of this data. Now, this is very simple. You're going to write the equation. At the top of the screen, it gives you the equation. Y equals ax plus b. Copy it down. Then you copy the a value in, and it'll tell you what to round to. In this case, it says nearest hundredth. So y equals 1.33. X plus my b value, which is negative 27.98. And there you have it. You are done. You have rounded the coefficients to the nearest hundredth. Part B says, using your equation from Part A. So now using this equation, determine how much weight of a salmon, determine the expected weight of a salmon that is 30 inches long. Again, this is simple. You're just going to take 30 inches and you're going to say, okay, was the inches the x value or the y value? X obviously comes before y. And if I match up my units, it looks like the inches, so I'm just going to plug 30 into the letter x. And then slam bam, type that in your calculator, and notice I get a predicted value of 11.92 pounds. C says, using your equation from part A, determine the expected weight of a salmon that is 52 inches long. So obviously you would do the same thing. You would plug 52 into the inches, which is the X value, and come up with a solution. Now, we've talked about this correlation. I want to highlight this R value. Let's go ahead and jot this R value down. This is 0.9839. 4 decimals is probably fine. Again, this is that correlation coefficient. What is this telling me? Well, there is a strong relationship between the length and the number of pounds a salmon weighs. Okay, and it is a positive strong relationship. We can add that word in there because this is a positive number. So the slope should be very close, or the scatter plot should be going up. Okay, we said we're going to cover lots of different regressions. Here's the next one, the exponential regression. So you should be familiar by now with exponential growth and exponential decay. Exponential growth starts growing slow, but then rapidly grows very, very fast. I can draw one line of best fit in. So when you're asked to draw exponential growth, that is what we are looking for. When we say exponential decay, it should start very high, but then grow and come downwards like this. Exponentials, you'll recall, do have asymptotes. That's why it looks like it's bending that way. So our next example here. The population of Jamestown has been recorded for a selected year since 2000. The table is given below. Part A, use your calculator to determine a best fit exponential equation. Highlight that for yourself. It is no longer linear. We are looking for an exponential equation. Now here's one trick they have on you. X represents the number of years since 2000. So they don't actually want you to type in 2002 because they're telling you, and it doesn't happen in every problem, you have to read, X represents the years since 2000. So 2002 is actually 2 years since 2000. 2004 would be 4 years, 5 years, 7 years, and 9 years. So to be clear, you are not using those years. So obviously again, L1, L2, this represents X, this represents Y. Let's go ahead and get that typed in our calculator. And it does say round A and B, round A to the nearest integer and B to the nearest thousandth. So this time, I'm not going to pick linear because it specifically asked for exponential. So as I scroll down, it looks like that's on my 0 key. Again, make sure you use L1 and L2 because you used both, and we're going to carefully write this out. So I'm going to start by copying down the formula it gives me. A times B to the X. Y equals, it says the A value to the nearest integer, so 5158. My B value to the nearest thousandth, so 1.041 raised to the X. There you have it. It's that simple. You are literally copying off that screen. Part B says sketch a graph of the exponential function that you just have and label your window and y-intercept. So I'm simply going to sketch this function. When I plug 0 into this equation, anybody to the 0 is 1. So my y-intercept is 5,158. So I might count by thousands. That's 5,000, maybe is there, 4,000, 3,000, 2,000, 1,000. And you should see that that function shoots up. Obviously, you can graph it in your calculator, and it looks something like that. B, by what percent does your exponential model predict the population is increasing per year? Okay, so great question. So let's rewrite that down. So I have 5158 times 1.041 to the X. So first of all, remind yourself, this number represents your initial, and this is my growth. Okay, now the first thing is it exponential growth or decay? Well, obviously from the function you can see that it's exponential growth, but recall that that formula is y equals that initial amount, 1 plus or minus the rate to the time. So since that number is greater than 1, I know that it's growth, and I can simply do 1.041 minus 1 to get me a 0.041. So it is growing at a rate of 4.1%. It says algebraically determine the number of years for the population to reach 20,000. Okay, so I'm going to look back at my table. 20,000, it says, is the population. Is that my X or is that my Y? Well, just reading across the table, that is my Y. So I'm going to carefully plug 20,000 in there. Okay, great review. Remind yourself that this exponent, box it in, is only on this number. So the first thing you have to do is get rid of this 5158. So to do that, notice it says times. I'm going to divide each side by 5158. And I get 1.041 to the x. Get a pretty ugly looking number, 3.877. You cannot round in the middle of a problem, so immediately I'm going to store that into alpha a. So I'm going to say a equals 1.041 to the x. Now recall this is an exponential equation because that exponent is where the variable is. The only way to solve an exponential is to take the natural log or log of both sides. When I do that here, I'm going to get the ln of a. You can use common log if you want as well. When I put the ln in front here, remember that exponent is going to come down in front. So I'm going to get the ln of 1.041. To solve for x, I'm just going to divide both sides by the ln of 1.041. And I get x equals 33.726. My units, of course, would be years if I look at that table, and to the nearest year would get me a total of 34 years, just because it says round to the nearest year. All right, our next regression is called sinusoidal. Hopefully that rings a bell and you're thinking sine curve in your head. So again, our regression is just going to go through as many as it can. It's certainly not going to hit all of the points or be exact, but it should be periodic. That is the key word. It should have a periodic flow, a period to it, something that repeats. So this temperature of a chemical reaction changes during the reaction. The temperature is measured every 2 minutes, and the data is shown in the table below. So again, this represents my x, my y, L1, L2. Why does it seem like this data might be periodic? Well, you notice it starts at 35, 38, 41, it goes up, then it starts to come back down, but then it looks like it's going back up again. So because it has that pattern, it goes up and down and up, I'm thinking periodic. Create a quick scatter plot using your calculator to verify. So I quickly typed it in my calculator so you can verify that it is periodic. It does have that up and down behavior. So now it says use your calculator to do a sine regression. So they are telling you what to pick. A sine regression that looks to be in this form. Round all parameters to the nearest tenth, then graph your data to informally assess the fit of the curve. So this time when I go over to calc, make sure you arrow down until it says sine regression. It looks like it's on C on my calculator. I'm picking sine regression. Now this screen will come up. Iterations, I believe the calculator automatically puts it at 3. I think you can put anywhere up to 16. I would just leave it at 3. And again, make sure you have L1 and L2 in there. You don't need to put the period in. It will take over for you, and then obviously calculate. So you'll see, hopefully yours spit out the same thing. It did say round to the nearest tenth, so remember A stands for amplitude, so I'm going to say 3.9. The sine of my B in this case is 0.39, x minus 0.72. And at the end I have that vertical shift or midline of a positive 38.50. Okay, so again, amplitude, frequency, phase shift, and my vertical shift or midline. Okay, so now we got to be careful with these questions. According to your model, what is the range of temperatures for the chemical reaction? So it's saying using your model. My range would be my min and my max. Okay, so remember you have to start with your midline, which in this case is 38.50. And to get my highest, I would add my amplitude. So I'm going to add my 3.85. And to get my lowest, I would take that midline and subtract my amplitude. So I'm going to subtract 3.85. And those two numbers make up my range. So according to our model, the max is 42.35 and the minimum height is 34.65. According to our model, what is the time it takes to complete one full cycle? Well, remember, that is that one full cycle key is the definition of period. What is the period? Well, that's 2 pi over my frequency. So in this case, that's 2 pi over 0.39. And if I type that in, I get 16.11. So does that make sense? Does it approximately look like 16.11 where it repeats? Well, look. From 35.7 back to 35.9, I would agree that looks like one complete cycle. All right, next example would be quadratic regressions. And hopefully you've guessed it, a quadratic function is obviously another name for a parabola. So I have two staring at you. If I were to try to draw the line of best fit, hopefully again it goes through most of the points. In this case, this ax squared, this a value would be positive greater than 1. In this case, this frowning parabola of ax squared, my a value would be less than 1. So same idea, the cost per widget introduced by a factory generally drops as more are produced, but then starts to rise again over time. So they give me this nice table of widgets, number of widgets and cost. And why should a quadratic model be considered for this opposed to a linear exponential? Well, that's a great question. Well, notice it starts high and then it gets low, but then it starts to get high again. So what function, try to draw it out. I start high, I get low, but then I get high again. Would you say that represents a quadratic? A linear would only strictly get high or strictly get low, and an exponential again would strictly go up or strictly go down. But this quadratic is going to go up and down. So this time it says you can create a scatter plot on your calculator, but let's go ahead and let's get the quadratic regression. And we'll round everything to the nearest tenth. So you can follow my data. I chose quadratic regression this time, and here's my equation, so I'm going to copy that down, y equals ax squared plus bx plus c, and we said round all our parameters to the nearest tenth. Actually, just based off what I'm getting here, I'm actually going to change that to thousandth. So I'm going to go with 0.001 x squared minus 0.250x plus 16.863. All right, last question for the night here. The availability of leaded gasoline in New York State is decreasing, as shown in the accompanying table, where X is defined after years of 2000. So again, because they're telling me X is defined for years after 2000, 2000 would actually be 0 years after 2000. That would be 4, 8, 12, and 16. And I'm only doing that if they tell me so. So X is my year, Y is my gallons. So based on the scatter plot, what type of regression would best model the data? So we're going to go ahead and create a scatter plot to help us here. So I plotted the points on my calculator, and obviously you can plot them by hand. Now just looking at this, I think we can rule some of them out. Clearly, does this look sinusoidal? Does it look like the sine curve? That's out. Does it look like a quadratic? Hopefully that's out. Doesn't look like it's going up and down, or down and up. Then I have exponential growth is out. Maybe exponential decay or maybe linear. Those are the two that really stick out to me. So it kind of looks more like a line to me than anything else from what we see here. So it says find the appropriate regression equation with coefficient rounding to the nearest tenth. So I'm going to go ahead and get linear. So I'm getting y equals negative 6.2x plus 150.4. Now, how do I know that I'm kind of accurate here? Well, I'm going to use that R value, my correlation coefficient, and it was negative 0.998. I would say, wow, that is pretty darn close to negative 1. That is almost as strong as I can get. So, you know, that's telling you this is a really good relationship. Negative, because the slope is negative, right? The slope of that line would be negative. And 0.998 is pretty darn close to 1. So I think we nailed it and we picked the right one. Using your equation, how many gallons would be left in 2018? Well, careful, we're not going to plug in 2018 because X is years after 2000, so I'm only going to plug in 18. And of course, that's a year, so that goes into X. So Y equals negative 6.2 times 18 plus 150.4. And I get 262 gallons. Obviously in thousands. Let me make a note, in thousands. If this relationship continues, during what year would the first leaded gas become unavailable? Well, if it's unavailable, then how many gallons would you have? You've got it. You wouldn't have any. So I would set that equation equal to 0 and solve for X. So I'm going to subtract that negative 150.4 over and then divide by that negative 6.2. And I get 24.25 years. So notice the question said during what year? And remember, that's years since 2000. So I would say during the year 2024. And E, we'll just go ahead and set up. Using your equation, when will 2,500 gallons be left in New York State? So obviously gallons is my y, so 25,000 equals that negative 6.2x plus 150.4, and then we would solve for x. Well, I think that does it for us. We've covered several different regression equations, and we'll get some good practice tomorrow. Have a great night.